Okay, the last part of this Module 5 is something that's a little different, and I don't know, sometimes it can be a little confusing or a little tricky. It's called Graphene by Transformations. And you noticed here, I've gone ahead and written down a function, f of x equals negative, parenthesis 2x minus 3 squared plus 2, or just to make it clear, f of x and y are interchangeable. You could think of it as y equals negative 2x minus 3 squared plus 2. Now, if we were asked to graph this, here's something you can always do. And that is you can always learn, or you can use the first method that you learned to create graphs, and that's by doing a data table. So just so you know, the old methods, the old rules still apply. So in other words, you can choose some values for x. If I said x equal to 0, this is minus 3 squared, which is 9, minus 9. I think if I'm doing this correct in my head, if x is 1, it's minus 1 squared, which is 1 minus, it's 1. If I do negative 1, it's negative 2, negative 5, ooh, 25, it's like maybe minus 23. Anyways, and you can go plot these points, right? And if you plot enough points, then you can probably figure out what this graph looks like. All right, so that's a traditional way to graph. However, they don't want to do that here. They want to do something different. And here's what they're going to do. If you're given an equation like this, what they want to do is go back and strip it down to what they call the parent function. The parent function is usually just the variable part. So in other words, it's plus 2 here for now. I'm going to sort of toss it aside. If I look inside here, I'm going to sort of get rid of the minus 3. I don't want the 2 there. I don't want to mess with this negative. When you strip away everything but basically the variable, you end up with the parent function. And what they're going to do is they're going to go sort of graph this parent function. And then, starting with the parent function, we're going to now, one piece at a time, start adding things, subtracting, whatever I have to do to end up transforming this back into my original function or equation. And as I do each step of this, I'm going to go on a graph and I'm going to determine what each step would do to the graph. And after I'm done with my 3 or 4 or 5 steps, then wherever the graph ends up, then I'm done. Now what I'm going to use, I have a little cheat sheet I've used for a long time. Looks like this. So when I do an example in a minute, you're going to see me use this. If this is something that you might find helpful, you can let me know and maybe I can post it in Ivy Learn. But this, you notice over here they have what they call the original graph. And they just made up sort of a graph here. And then they have 2 sections. You notice the left-hand side, it's called outside the function. And then the right-hand side is called inside the function. What that means is inside the function means all the things you do that directly affects or changes the variable x. And outside the function, it does not affect x directly, but indirectly you're doing stuff to the whole function. So in other words, here's a graph and here's f of x. Outside the function, this first example says in this case, they added 2 to the function, f of x plus 2, or over here, f of x minus 2. And for each of these actions, it tells you what the effect is of your graph. So, for example, is this my original graph? They just made it up, f of x. If I take that function and add 2, they say the effect is it shifts the graph up. So if you compare the original graph to this graph, you can see it's moved up 2. Adding 2 here causes the graph to shift up. If I had subtracted 2, then you could compare, and you can see how it would cause the graph to shift down. Here you see the effect if you multiply your function by a number. In this case, they call it a vertical stretch. So if you compare this to this, basically it's like they double the size, stretching it up and down. It doesn't become any wider. It just gets stretched from top to bottom. Or you can see if you multiply by 1/2, so if you multiply by a fraction less than 1, it actually squishes it. And then the last thing they sometimes do is they might stick a negative sign in front of the function, and that causes it to flip. It flips around the x-axis. So those are all the things that can happen outside the function. Now I want you to compare it with over here inside the function, where you notice outside the function we added 2 to the function. Here they actually change the x. They go inside the function and add 2 to the x and then look at the function. So when you change your variable x, that's called inside the function. In this case, if you add 2 to x, what's the effect? It shifts it left. Here's the original graph. When they added 2 to the x inside the function, it moved the whole function 2 to the left. Sort of the opposite. Maybe you think if you add positive 2 to x, it moves it to the right, but it's sort of backwards and moves it to the left. And look what happens if you'd happen to subtract 2 from x. That causes it to move to the right. Now down here, you notice we multiplied 2.5 outside the function. Here, we multiply x by 2, so this is happening inside the function. And then we multiply x by 1/2 inside the function. The effect of this is a vertical squish. So it squishes it half the size, pushes in the sides. Although if you put a 1/2 in here, it actually stretches it, makes it twice as wide. And then over here, we put a negative in front of the function here. If you put the negative inside the function, it's a horizontal flip, which means it just flips around the y-axis. So that's a lot of stuff going on here. It's a lot of stuff to remember. So now, let me show you graphically the impact. So here, in a few minutes, this is going to be my sort of parent function. Just a basic f of x equals x squared. This is what that graph looks like. What I'm going to do here is just do a few quick simple examples so you get a feel for it. So here's my original function, x squared. I want to now actually graph x squared plus 2. And I've actually got a red pen, maybe you can see it. Now what this is, I'm adding 2 outside the function. And just in case I forget, when you do something outside the function, and in this case you add to it, it shifts it up that amount. So I've got to take this graph and basically move it up by 2. So this point goes up 2, this point goes up 2, this point goes up 2. So the whole graph gets just shifted by 2. And if you try and now draw this, may not be a perfect graph, but you can see the whole graph has shifted up 2. That's the effect of when you add 2 to your parent function. Here's another, here's another one that we can look at. How about Same parent function. Now we add 2, but it's inside the function. I'm actually changing the value of x. If I go to my cheat sheet, just to make sure I don't forget, when I add a number to the x, so it's inside the function, the effect is to shift it left. So therefore, I'm going to shift this graph to the left by 2. So now that point goes here, this one goes here, this one goes here, maybe this one is here. And then you can see how the whole graph, I've moved it or shifted it to the left by 2. That's the impact of adding 2 to the x inside the parent function. One last example, just to sort of understand it. How about if I stick a negative sign in front of the functions? This is outside the function. Now look at my cheat sheet. We add a negative outside the function. They say it is a vertical flip, which means it just rotates around the x-axis. On this case, I think you can look at something like this. It's almost like it's a mirror image where if you take this graph and just fold it over, it would look like this. All right, all that said, to now go ahead and try and actually, I'm going to graph this function, but I'm going to start with the parent function. So I'm going to strip everything away, and then starting here, build it back up one piece at a time until I get to here. And each piece I add on, I'm going to go and see what the impact is of my graph. So here is my initial graph. Let me start with a new piece of paper. Try and keep this nice and clean. So here is my final function or equation is going to be this. That's where I want to end up, but I'm going to start with what's called the parent function. Strip everything else out but just the x. And what you do is you work from the inside out. As you start taking the parent function and trying to create your end product, you do it one piece at a time, but you work from the inside out. In other words, first thing I'm going to do is I see I have 2 times x. Actually, I think, yes, 2 times x. So I'm going to do 2 times x, this whole thing squared. So that's adding in the 2. Now to go from here to here, if I go to my cheat sheet again, this is inside the function. So this is inside the function. I've multiplied by 2. Inside the functions over here, you multiply by 2. It squishes it. I think it makes it half the size it was. So if I go to my graph, now it's like half the size means if this is here, it goes here. This is here, it goes here. Maybe this point goes to here. So it's like it's going to become a lot narrower because I'm making it half as wide. So I'm not going to draw it, but I could say now, so this is a graph. If this is x squared, this first graph is actually 2x quantity squared. Now, what I want to do next is, working from the inside out, I'm going to go ahead and subtract 3 from the 2x. Once again, when I subtracted this 3, it's like I'm inside the function because I'm inside this squared. So once again, this is an inside the function action, and I'm subtracting 3. So if I go to my cheat sheet, when you subtract a number inside the function, it's right here, it shifts it to the right. So I go back to my graph, and I'm going to shift it to the right by 3. So this point is going to go 1, 2, 3. This point is going to go 1, 2, 3. This point 1, 2, 3. This point 1, 2, 3. This point 1, 2, 3. Up here 1, 2, 3. And 1, 2, 3. This starts to get a little messy, but hopefully I can keep it all straight. So this now is where my graph is sitting after applying this. And now the next piece I want to do is I'm going to tack on the minus. Now this is outside the function. So you can see I'm building this up one piece at a time until I get to my final goal. So this is outside the function. So what's the effect of putting a negative outside the function? Here's outside the function. The negative here, it says it's vertical flip. You rotate it around the x-axis. So I'm sitting right here, so I need to basically flip it over. So I'm trying to draw a few points here. And these are like 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So now, something like this. So now my graph is sitting right here. And then actually I believe there's only one more thing I have to do. If I compare this to this, the last thing is to add on 2. And that is outside the function. So I go to my cheat sheet and say, what's the effect of adding 2 outside the function? It's right here, outside the function, adding 2, it shifts it up. So now I'm going to take, now I'm sitting here right here, and I got to move this up 2. So this goes here, this goes here, this goes here, this goes here. Now it's actually quite the mess, but that actually is your final graph. To be honest, it seems a little crazy, and to me it's not my preferred way of graphing, But it's something that they want you to learn, and in future math classes, this is something that might be of help to you, so that's what it is. Now there's one more kind of problem they do, which involves transformations, and that's where, so this is going to be like a homework problem, so let me do one real quick so when you do it, you won't be confused. Because what they do is, let me find the problem I want to do in my notes here. I have a mess here. All right, here it is. They basically give you, this is like a quadratic equation. And what they want you to do, you've done this before for other reasons, they want you to use this procedure called completing the square. Because when they do it, here's what they want it to look like. I'll write it like this. I don't know if the book uses this designation, but basically, I want to take this equation and rearrange it, rewrite it so that I have parentheses squared, and I need to figure out what A is, what H is, and what K is. These are going to be numbers. And once I do this, then they want me to graph it by doing the transformation. So let's just go and do this example. So I've got to complete the square. Now the first thing, hopefully you remember by completing the square, I can only complete the square. I cannot have a coefficient or a number in front of the x squared. For me to go through the procedure to complete the square, I cannot have a coefficient here. So how do I get rid of it? Well, how about I divide both sides by 2. I can do that in math. I can do whatever I want as long as I do the same thing to both sides of the equation. So when I do that, over here on the left I have f of x over 2. Over here I have x squared minus 6x plus 10. So now I don't have a coefficient here, so I can go ahead and now try and complete the square. Now if you remember, what you do when you complete the square is you take the coefficient of your middle term, you go off to the side and you do what I call a special calculation. You always divide it by 2, and then you square that quantity. 6 divided by 2 is 3, 3 squared is 9. And let me rewrite this. Now I'm going to take that 9 and I'm going to stick it in right here, plus 9. Here's my plus 10. Now, I've added 9 to this equation. Well, I can't just do that without either adding 9 to the other side, or actually, something I'm going to do, a little trick, it's not too confusing. Instead of adding 9 over here, how about I go out here and I subtract 9? Right? 9 minus 9 is like 0. So I haven't really changed this, but I have stuck this 9 in here. Because the reason I want to do this is because now this is a perfect square trinomial, which I can factor. And it always factors the same way. It's always parentheses squared. You've got your variable. Whatever the sign here is what goes down here. You take this number, you take the square root of it, and that goes here. So x minus 3 quantity squared equals x squared minus 6x plus 9. Now I still have this over here, 10 minus 9 is 1, so I've got the plus 1 here. Now, I want this thing to be f of x, so I need to get rid of this 2 here. So actually, if I multiply both sides of the equation by 2, then the left-hand side gets back to f of x. I distribute the 2 times this whole thing. I'll just leave it outside the parentheses. And then 2 times 1 is plus 2. And now I've accomplished my goal, because here's the equation I started with. My goal was to rearrange it to have parentheses squared and this stuff here. And that's what I've done. So now I want to graph this using transformations, which is sort of crazy because now I'm going to have to break it down into the parent function. You get rid of the 2, the -3, the 2, and you strip it down to x squared. Now let's see if we can do this pretty quickly. If I build it from the inside out, first thing I'm going to do is I'm going to subtract 3 inside the function. So I happen to have another starting graph of x squared. So if I subtract 3 inside the function, if I look at my cheat sheet, that means I'm going to move 3 to the right. I'll just use my black pen. 3 to the right means 1, 2, 3. I'm going to go here, 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 here. So there's the first step. Then I'm going to multiply by 2. This is outside the function. I go to my cheat sheet, multiply 2 outside the function. Vertical stretch, so like you double the size, which is going to be a little strange for a parabola. So like, I think this point goes, if you double it, it's 1, it goes to 2. This one is like 4, it goes to 8. So this goes here, this goes 4, 5, 6, 7, 8. So it almost like makes it skinnier because you're stretching it out. So the effect is it makes it look skinnier because you're doubling the size of it. And then the last thing you do is add 2 outside the function. That means you move it up 2. So this is getting messy here. This goes here. This goes here, here, up here. You can see why it's not my favorite thing to do. It gets messy, can be a little confusing, and anyways, you can't even really see it, but somewhere in here is a graph of this. So once again, that problem was they start out with this quadratic equation. They want you to complete the square to rewrite it like this. And then once you get it like this, they want you to use transformations where you break it down and build it back up again. So hopefully on the homework you can easily understand it and see what you're doing. All right, so that's it for Module 5.